Hello everybody. Today we shall discuss about mathematical expectation or mean value of a random variable or a distribution. Sometimes we call it mean value or mathematical expectation of a random variable, or sometimes we call it mathematical expectation or mean value of a distribution. Both are same. What is this? Actually, suppose if we want to consider the problem of a company which want to hire some a group of worker for their important project, and suppose they have limited time, and they have two different group of workers. Their performance can be measured by two different random variables having two different probability distributions. Okay. Now, that particular company would like to hire uh, that particular group which would be efficient in the sense of time and in its sense of some economical constraint. Okay, so within limited period of time and within limited budget, the company would like to select the particular group of worker which will give them the best profit in that project. All right. So in such problem, just you see the individual workers, the performance of individual workers may be different, but altogether that company would like to concentrate on the performance of that group, the entire group. All right. The we need to study over here the quality of the entire group, the quality of the entire group, not the performance of a single group. All right, not the performance of a single element of that group or the performance of a single worker in that group. Hmm. We need to have certain mathematical measure by which we can make the decision about the quality of the entire group. All right. So that kind of qualitative measure, we are going to study that kind of qualitative measures and which will give us a particular answer to this problem. Hmm. And in order to get the answer to this kind of problem, we have the idea of mathematical expectation or mean value. Okay. It was firstly introduced by Pascal and Fermat individually in the year 1654, and later on, Huygens improved this idea of expectation and developed this theory of mathematical expectation in a book on the year 1657. Hmm. This much history we have. Anyway, so let's try to understand what is the mathematical expectation or mean value from mathematical point of view. Okay. So I just tried to express the idea of mathematical expectation. So mathematical expectation, different kind of mathematical expectations are there, and different kind of mathematical expectation represent different characters or the quality of a particular probability distribution. All right, and mostly it has very important application in the field of statistics. Statistics is one of the most important application of probability. Hmm. So over here, we are going to define the mathematical expectation or mean value of a random variable. All right. Now suppose we have a random variable x and we have a function of the random variable x. Suppose g of capital X is the function of the random variable x. Okay. and let us consider that the spectrum of x are given by xi, and corresponding mass function is given by fi. First, we are defining this one for discrete distribution, and similar definition we will have for continuous distribution. So whenever we need to define mathematical expectation, we need to define both for discrete as well as for continuous distributions. So at first we are considering this discrete distribution. So suppose the random variable x has a discrete distribution given by this kind of spectrum and mass function fi. Then the expectation of the function g of x, expectation of g of x is defined as the summation from I is equal to minus infinity to plus infinity g of xi multiplied by fi. Okay, just in place of g, we are in place of g of x over here. In place of this x, we are putting this expression, the value of the random variable x, that is xi. And then the total expression is multiplied by the corresponding mass function fi, and afterwards we are taking the total summation for all possible values of I. Over here I is generally theoretically, at least it should vary from minus infinity to plus infinity. Okay, so that is the idea of mathematical expectation in case of discrete distributions. Now, in case of continuous distribution, suppose the mass, in place of mass function, we have this density function f of x, and suppose the density function has the spectrum from minus infinity to infinity. Hmm. And then the expectation of gx is defined in this fashion, that integral from minus infinity to infinity g of x multiplied by f of x dx. Just very similar to this previous definition in case of discrete distribution. You see, in place of this g of xi, okay, we have g of x over here. In place of this fi, we have f of x over here. And as because we have a summation, so in place of summation, in case of continuous random variable, we have integration. Integration is a kind of continuous summation. Got it? So we actually have two identical or you can say equivalent definitions, not identical, rather we should say equivalent definitions for mathematical expectation of g of x. And in both of these two definitions, in case of discrete case we have an infinite summation, and in case of continuous case we have an infinite or improper integral. Got it? It is a type 1 improper integral. And we know that this kind of integral does not always exist. The convergence criteria for the existence of this kind of integral should be satisfied. And over here in these two definitions, in these two equivalent definitions, the infinite summation and this infinite integral, both of these two must be absolutely convergent, not ordinarily convergent. Okay, the definition says that both of these two, whether you consider infinite summation or this infinite integral, whatever it is, both of these two have to be absolutely convergent. If in case of any distribution the summation or the integral is not absolutely convergent, it may be conditionally convergent. That means it is ordinarily convergent but not absolutely convergent. Okay, even if the integrals or the summation, infinite summation or infinite integrals are ordinarily convergent but not absolutely convergent, then we say that the expectation does not exist here. So for the existence of the this kind of expectation, the corresponding infinite summation and infinite integral must be absolutely convergent. Be very specific about it. Hmm. And what is the reason behind it? It has some reasons related to the mathematical operations that we shall encounter in the subsequent study. especially this kind of mathematical manipulations are obtained in case of especially for especially for distribution of more than one random variables. Okay. Anyway, so let's continue over here. Now, it may so happen that if you want to find out at first the distribution of this g of x, the probability distribution of g of x, you can also find the probability distribution of g of x, and afterwards you can check whether the expectation of y, the expectation of y becomes is equal to expectation of g of x, and you will find that both of these two expectations are equal in value. So if you want to find out the expectation of g of x from the distribution of x, you will get this left hand side value. If you want to find out the expectation of g of x from the distribution of y, you would get this right hand side value. You will find that both of these two values are numerically same. Clear? So it doesn't matter whether you compute the value of this expectation from the distribution of x or from the distribution of y. It doesn't matter. Okay. And certain elementary properties have been written over here, that the expectation of a constant is equal to that constant itself. Expectation is a linear function. These two are linearity property. Some constant multiplied by gx, its expectation is equal to a into expectation of gx, and over here expectation of gx plus expectation of hx is equal to expectation of gx plus hx is equal to expectation of gx plus expectation of hx. So both of these two together form the linearity property. You see, expectation is actually defined in terms of summation and integration. So summation and integration both are linear operators. That's why expectation would follow the linearity property. Okay, and we have another result, that expectation of gx, its modulus, is less than is equal to expectation of modulus gx. Okay, that is one property. And the next property is that if gx is greater than is equal to 0 for all x, then its corresponding expectation of gx should also be greater than is equal to 0. Along with that, further, if when the non-negative function, if we have a non-negative function gx such that the expectation of that non-negative function becomes is equal to 0, then we must have gx is equal to 0. Only fact that we shall have is that gx should be is equal to 0. Okay. For example, over here, you see, let's consider the gamma distribution. We shall consider the gamma distribution. The computation of gamma distribution is very easy. That's why we shall mostly study very elementary examples through this gamma distribution. So let's consider a gamma variate x having parameter L. And then we need to compute expectation of root over of x. How can we compute it? This is the density function of gamma distribution. Then expectation of root over of x should be theoretically from integral from minus infinity to infinity. Gx means root over of x. All right. So over here, root over of x into fx dx. And you see, in case of this density function, you observe over here that this f of x, you see, I made a printing mistake over here. This f of x is equal to 0, and therefore if we want to decompose this integral, this infinite integral from minus infinity to infinity, then we can decompose it from minus infinity to 0, that is the first integral, and then from 0 to infinity, that would be the second integral. And in this range, when x varying from minus infinity to 0, okay, in this range when x varying from minus infinity to 0, in that range, you see the value of the density function is equal to 0. So we should put a 0 over here. That 0 should come over here. I made this printing mistake. So 0 into dx should come over here. And in the range from 0 to infinity, in this range, this expression of the density function should take place. So minus infinity to infinity e to the power of x into, and this is the expression of f of x e to the power of minus x to the power of l minus 1 divided by gamma l dx. Now, as because this is actually 0, therefore the contribution of this expression, this much contribution would be equal to 0. So effectively, we shall have only the contribution from this second integral. We find that this expression becomes is equal to e to the power of minus x to the power of l plus half minus 1 divided by gamma l. And this is actually this numerator expression. We can compute, we can consider this gamma n outside the integral sign, and the numerator expression would be actually gamma half function. So this would be the expectation of root over of x. So in this way, we compute the expectation of a function. Next, we define mean of a probability distribution or mean of a random variable. What is this? The mean of a random variable x or that of a distribution of x is defined as this. It is denoted by expectation of x. Expectation of x is defined as the mean of x. Okay, expectation of x is defined as the mean of x. It is generally denoted by m within bracket x, or sometimes we write it as m suffix x, or simply by the notation m. We generally define or we denote this mean of x by these three notations. Mostly we use this notation m. Clear? So m is equal to the expectation of x. All right. And this is actually, you see, this is called the measure of location. Why it is called the measure of location? Because it can be proved that this kind of summation actually represents the center of mass of the probability distribution. Center of mass. I told you about the probability distribution. The probability distribution can be considered as if some one unit of mass has been spread from minus infinity to plus infinity. And if you consider, suppose we have some probability mass over here, discretely distributed, suppose. And in that case, if you consider their center of mass, you will find that the formula for evaluation of the center of mass will involve this expression. This would be the formula for computation of center of mass of the probability distribution. Okay, and ultimately that's why this is this kind of expression, that is actually the mean of x. This kind of expectation is actually the mean of x, is called the measure of location. If probability mass has a particular kind of character, that the entire distribution, entire probability distribution can be thought of situated at the center of mass G. We can consider that entire probability distribution can be thought of situated at the center of mass G. Got it? That's why this kind of measure is actually called a measure of location of the probability distribution. There are other measures of location that we shall study in the subsequent lectures. One such measure is called median. Another measure is called mode, etc. We shall study them later on in the subsequent lectures. Okay. Now let's try to find out the mean of some standard well-known distributions. And in exam you will find this kind of questions, mostly this binomial distribution, Poisson distribution, normal distributions. Mostly in the previous years this kind of questions were selected, and in this new syllabus, the few new kind of distributions have been introduced, like in geometric distribution, Pascal distribution, and all. So we need to study the mean of all different kind of distributions. In this lecture, we shall study some of these mean mean of the few distributions, and I shall leave some deductions for you as a homework. Hmm. So let's firstly try to understand what is the mean, try to understand how to deduce the mean of a binomial distribution. So what is binomial distribution? We know that in case of binomial distribution, what is xi becomes is equal to I, where I varies from 0 to n. In case of binomial NP distribution, I generally varies from 0 to n, and the probability mass function Fi, this is denoted by NCI, p to the power of I into 1 minus p to the power of n minus I, where I again varies from 0 to n. Okay, so in this way we define the probability mass function of a binomial NP variate x. Now, what is expectation of x? You see, in place of x, we will have to write xi, and in over here, that xi has to be multiplied by this fi. So we shall have xi fi, and along with that, we shall have the summation from I is equal to minus infinity to infinity. But practically, in case of binomial distribution, particularly in case of binomial distribution, I would vary from from 0 to n, not from minus infinity to infinity. So this is actually a theoretical definition. From the theoretical definition, we obtain this range. But whenever we need to consider this particular case for binomial distribution, we shall have to restrict the corresponding values of I given by this range I is equal to 0 to infinity. So this theoretical summation, although it was an infinite summation, so in this case, as because only we have I is varying from 0 to n, so the summation would be a finite summation. Got it? And what is xi? Xi is equal to I over here. So we are putting the value of xi. We are now putting the expression of fi over here. So this is the expression of fi, that is NCI p to the power of I into 1 minus p to the power of n minus I. Now if we put I is equal to 0, for the first time in the summation, if we put I is equal to 0, you see this entire term corresponding to I is equal to 0 would be vanished. And over here, for the simplicity of the calculation, we have written this 1 minus p is equal to q. So this expression becomes p to the power of I, p to the power of n minus I. Now we are putting I is equal to 0. For I is equal to 0, the first term would vanish. So the first term becomes is equal to 0. And in the next and subsequent term, I would vary from 1 to n. Got it? This is the remaining expression. The remaining expression is not changed at all. Only this NCI has been decomposed in factorial of n divided by factorial of I into factorial of n minus I. And you observe that this one single factor I will be cancelled with a single factor I in this factorial of I. So we shall have only factorial of I minus 1. And this factorial of n minus I has not been changed at all. From the numerator, one factor n has been taken outside this summation over here. That's why we have factorial of n minus 1. And from this p to the power of I, one single p has been taken outside this summation. That's why we have p to the power of I minus 1. And remaining q to the power of n minus I has not been changed at all. Okay. Now you see this, if you look at this expression can be written in this way, that can be written as n minus 1 c I minus 1, the combination. N minus 1 c I minus 1. And over here, this expression n minus I, this expression can be written as n minus 1 minus of I minus 1. Clear? So you see, if we consider this k is equal to I minus 1, whenever I is equal to 1, the value of this index k would be equal to 0. Again, whenever I is equal to n, the value of the index k would be is equal to n minus 1. So in this way, the summation will change from k is equal to 0 to n minus 1. Again, this I minus 1 in place of I minus 1, we can write k. Therefore, we shall have p to the power of k in place of p to the power of I minus 1 and q to the power of n minus 1 minus of this k. In place of I minus 1, we have this k. Hmm. And if you observe that this expression within this summation, this expression will be actually the binomial expansion of the p plus q to the power of n minus 1. Got it? This would be actually the binomial expansion of p plus q to the power of n minus 1. Okay, and what is p plus q? We have taken q is equal to 1 minus p. Therefore, p plus q should be is equal to 1. So if we put p plus q is equal to 1 over here, only we shall have n multiplied by p. So this is the result that np is the mean of the binomial distribution. Here, np is the mean of the binomial distribution. Now, similarly, for Poisson distribution, this is the xi is equal to I is the is the spectrum of the Poisson variate x, and fi is equal to e to the power of minus mu, mu to the power of I by factorial of I. This is the probability mass function of the Poisson mu variant. So if we want to compute the expectation of x, this is the definition of the theoretical definition: I is equal to minus infinity to infinity. However, if we particularly consider this range over here, I varying from 0 to infinity. That's why we shall have to consider I varying from 0 to infinity. So in place of xi, we shall have to put I only. This is the value of xi. Xi is equal to I. So we have to xi is equal to I, and in place of fi, we have the corresponding expression e to the power of minus mu, mu to the power of I by factorial of I. Again, in this case, we have the result that if we put I is equal to 0, then that term will be equal to 0. That's why we have taken this, written this one separately. And in the remaining summation, I would vary from 1 to infinity. Got it? And in this summation, if we consider this I, you see over here, this one single I will get cancelled with this factorial of I. So we shall have factorial of I minus 1. Now this e to the power of minus mu can be taken outside the summation. So we have e to the power of minus mu, and we have taken only a single mu out of this e to the power of mu, mu to the power of I. We have taken this single mu from this mu to the power of I. Therefore, we shall have mu to the power of I minus 1. Now again, if we consider k is equal to I minus 1, just similar to the previous deduction, if we consider k is equal to I minus 1, then you see we have this kind of summation. Summation k is equal to 0 to infinity mu to the power of k divided by factorial of k. And this summation is nothing but is equal to e to the power of mu. Got it? And we already have e to the power of minus mu multiplied by e to the power of mu. Therefore, they would together cancel, and ultimately we will have this mu. So hopefully it is clear that this parameter mu has some special significance. That this parameter mu represents the mean of the of this Poisson distribution. Got it? So in each and every distribution, you will ultimately find that the mean and different characters that we shall discuss in the subsequent lectures, all of them will be represented by their parameters. So over here, mu, the parameter of the Poisson distribution, represents the mean of the distribution of x. Similarly, we have the negative binomial mean of the negative binomial distribution. I am leaving this deduction for you. Got it? There are certain calculation involved, so I would suggest you to please go through this calculation by hand. because these calculations are not easy calculations at all. So different kind of summations have been involved in this kind of calculations, and so I would request you all to please go through this calculation, and ultimately you will find that in case of Poisson, in case of Pascal distribution, expectation of x becomes is equal to RQ divided by P. What is Q? Over here again Q is equal to 1 minus P. Got it? Q is equal to 1 minus P. So you can write it as RQ divided by P. That would be the expectation of x. All right. And particularly if we put R is equal to 1 in this negative binomial distribution, you will get the geometric distribution. So I am leaving this one again for you. Just by putting R is equal to 1, you will get the corresponding mean value of the geometric distribution. Now we consider the mean of a normal distribution. That is one of the most important distribution that is called the normal distribution. Let's consider a normal m sigma distribution. This is the density function of a normal distribution, and the spectrum is from minus infinity to infinity. Generally, we define sigma greater than 0. Why sigma greater than 0? That we shall understand. We should try to understand, because sigma has a special significance that would be clear hopefully in the next lecture. Today we shall get some interpretation about this parameter small m. Okay, let us find the expectation of x. Theoretically speaking, expectation of x should be is equal to integral from minus infinity to infinity, and as because it's an expectation of x, so we shall have x multiplied by fx dx. And now we are putting this expression of fx over here, and therefore we shall get this type of expression. This type of integral x was there previously, and this is the density function 1 by root over twice by sigma e to the power of minus half x minus m by sigma whole square. This much is actually the exponent. Okay, e to the power of minus half x minus m by sigma whole square. Now over here we are decomposing this x in this fashion: x minus m plus m. We are writing this x in this way: x minus m plus m. So we are considering this x minus m in a single integral, and the remaining m is considered in this kind of second integral. Okay, over here you see, let me decompose this screen. Over here, let us now put z is equal to x minus m by sigma in these two integrals. So x minus m, this x minus m would be is equal to sigma into z. Got it? That's why in place of x minus m we got sigma into z, or z sigma. And x, as x being from minus infinity to infinity, m is any real number and sigma is a positive quantity. Therefore we can say that z should also vary from minus infinity to infinity. So in terms of z, the corresponding range is also from minus infinity to infinity. And the remaining expression over here, in place of this x minus m by sigma, we just put z. So e to the power of minus half z square would appear, and in place of dx we shall have this sigma dz. Therefore we have this kind of expression that this kind of z into sigma multiplied by this kind of density function. And you see this sigma will get cancelled with this sigma, so only we shall have this sigma outside this integral sign, and we shall have z 1 by root over twice by e to the power of minus half z square dz. Plus this m has been taken outside this integral sign over here. So m has been written in this fashion, and the remaining expression is 1 by root over twice pi e to the power of minus half z square. Okay. Now you see this integrand, the first integrand, this first integrand z into e to the power of minus half z square. You see, this is actually an odd function. So if we want to integrate symmetrically by this kind of range, minus infinity to plus infinity, due to the fact that this integral is an odd function, the total integral value of the integral would be is equal to 0. And what about this second integral? You see, if you look at this second integral little carefully, 1 by power of twice pi e to the power of minus half z square. This expression is actually the density function of standard normal distribution. Density function of standard normal distribution, and we know that the integral of a density function of any distribution, the integral from minus infinity to infinity of any distribution, that value is equal to 1. Okay, integral of from minus infinity to infinity f of x dx, this kind of integral is always equal to 1. This is a restriction that is follows everywhere for any distribution x. So as because this is the density function of a standard normal distribution, therefore the value of this integrand must be is equal to 1. The value of this integral must be is equal to 1. Got it? And therefore the total computation will become is equal to m on the small m. So what we observe over here, you see that expectation of x is nothing but is equal to m. So the parameter has a special meaning that m represents the mean of the distribution, mean of the normal distribution. Got it? And similarly over here, in case of gamma distribution, you can observe that this is the density function of gamma distribution. And so in place of fx, if we put the density function, you see this density function, this range from minus infinity to infinity can be further decomposed into the range from minus infinity to 0 in this kind of range. And then along with that, union of this range from 0 to infinity. So in this first range from minus infinity to 0, the value of this density function is equal to 0. That's why we have this 0. Okay, and in the remaining range, that means from 0 to infinity, in this remaining range we just put the expression of this density function. Okay, and if we make the computation, we will find that the finally we will have gamma L plus 1 divided by gamma L, and that value is equal to L. So this L, the parameter of the gamma distribution, stands for the mean of the distribution. All right, so L is the mean of the gamma distribution. Similarly, we have beta distribution of first kind and beta distribution of second kind. I am leaving the computation for your as your homework. You will find that in case of beta distribution of first kind, the expectation of x or the mean of x is equal to L divided by L plus m. And in case of beta distribution of second kind, the expectation is equal to L divided by m minus 1. And that's why in case of beta distribution, m, this parameter value m is generally taken greater than 1. Got it? M is generally taken greater than 1 because in the intermediate computation, m is to be assumed greater than 1. Alright. So if m is less than 1, in general, you see, in case of beta 2 distribution, we have the restriction that L greater than 0 and m greater than 0. So if suppose m is equal to half, then mind it, then the mean of the distribution does not exist. All right, because in that case it can be proved that this integral is not absolutely convergent. Yes. And we have that is this distribution, the Kochi distribution, that is a very peculiar kind of distribution because in Kochi distribution we are going to show that mean of the Kochi distribution does not exist because of the fact that the infinite integral involved in the definition of expectation of x, this infinite integral is not absolutely convergent. You probably have got the mu test for absolute convergence of type 1 improper integral. So by mu test we shall prove that this improper integral is not absolutely convergent. How to show this result? And as because it is an exceptional case, this is important as far as the exam is concerned. Okay. Over here, this is the density function lambda by pi multiplied by 1 by lambda square plus x minus mu whole square into, and this spectrum is from minus infinity to infinity. Okay, and if we now consider the transformation z is equal to x minus mu, so in place of x minus mu we shall have z, and so that x can be written as z plus mu. Hmm? Dz and dx both are same. All right. So we can continue with these expressions, and we are separating this integral. We are separating this integral in this first integral, where only we retain this term z, and in this second integral we have mu. All right. You see, in this second integral, the value of the second integral is easy to evaluate. The value of the second integral is easy to evaluate. You would get that the value of this second integral is equal to mu. But what about the first integral? You see, over here, if you consider the mu test, over here, this is the integrand. This is the integrand z by lambda square plus z square. This is the integrand. So we have written this integrand as equal to g of z. Hmm? And if you consider the mu test, already we have a parameter mu in this distribution. That's why in place of mu I have taken mu 0. So we are taking mu 0 is equal to 1 in the mu test. That's why this expression z to the power of mu 0 gz, if we take the limit z tending to infinity, that value becomes is equal to 1. Okay, and we know when this value becomes less than or is equal to 1, when the this limit becomes less than or is equal to 1, this corresponding integral is divergent. In order to convergence, in order to get the convergence, this limit must be greater than 1. We get the value is equal to 1. Therefore, from this new test, we can conclude that this integrand is not absolutely convergent. That's why in case of Cauchy distribution, we say that expectation of x does not exist. Okay, in case of Cauchy distribution, expectation of x does not exist. All right. And one should observe that if you consider the principal value, if you do not consider the absolute convergence, if you just simply consider the ordinary convergence, and you are interested to find out the principal value, then you would observe that the principal value of this integrand would be is equal to 0. The principal value of this integral would be is equal to 0. Why? Because this integrand is actually an odd function. So if you want to compute the value of this integral considering the ordinary convergence only, considering the principal value only, then you will find that the value of this first integrand becomes is equal to 0. Therefore, ultimately, this total expression would be is equal to mu in the sense of principal value only. But in the general definition, this expectation of x does not exist. The last part in this lecture that today I want to discuss is the definition of moment. Hmm? What is this? We have different kind of moment. Generally, moment is defined about a real number a. Hmm? This a is generally a finite real number. Sometimes we define absolute moment. we sometimes define raw moment, we sometimes define central moment. So how do we define all these moments? Generally, the moment is related by with this we can with a positive or non-negative integer k. Hmm. So kth moment about a finite real number, kth moment about a finite real number a is defined as this kind of expectation. It is defined by this kind of expectation, that expectation of x minus a whole to the power of k. This is called the kth moment about the point a. Why about the point? Because we have subtracted this value of a from the variable x. So you can consider that we can consider the probability distribution, and suppose this is the position of the real number a, and with respect to this a we are measuring everything. So if this is the origin o, and this is the position of the random variable x, then we are measuring everything from a, as if we are shifting the origin at the point A, just by the transformation that x prime is equal to x minus A. Got it? So by this kind of transformation, as if we are shifting the origin at the point A, so we can consider this A as the new origin, and this expression has been put over here. Hmm. That's why, and this is called the kth moment about the point A. So it is actually measured as if we have an observer situated at this point. We have an observer situated at this point, and with respect to that observer, we are considering the distance, and that distance would be is equal to x minus a. That's why this is called kth moment about the point A. Remember, we shall have whole to the power of k in order to get kth moment. Hmm. And if we consider modulus of x minus a whole to the power of k, then we call it absolute kth absolute moment about a point or a finite real number a. Clear? This is the definition of kth absolute moment. Particularly when a becomes is equal to 0 in this definition, if a becomes is equal to 0, then we shall have expectation of x to the power of k, and that is called raw moment. Raw means about the origin we are taking the moment here. So this is called kth raw moment. Okay, and we have the idea of central moment. Central moment is defined with respect to the mean. Suppose n is the mean of the random variable or mean of the distribution. In that case, this is the definition of kth central moment, x minus m to the power of k, its expectation. So you see, in case of kth central moment, in order to define the kth central moment, this m must exist. For example, in case of Kochi distribution, we find that m does not exist at all. Here, that's why you need to be very careful about the definition of kth central moment. And in both of these two definitions, particularly in case of kth moment, this kth moment, the kth raw moment, is actually defined by alpha suffix k of x, or simply by alpha xk, or simply by alpha k. This is the notation of kth raw moment, and in case of central moment, we have the notation of mu k. Mu suffix k denotes the kth central moment of x, or sometimes we write it as mu x k, or simply by mu k. Got it? So these are the notations of kth central moment. And particularly, if we put k is equal to 0, so x to the power of 0, that is actually 1. Expectation of 1 is equal to 1. So you will get that alpha 0 is equal to 1. And what is alpha 1? Alpha 1 is equal to expectation of x, that is actually the mean of the distribution. So these are the standard results. Alpha 0 is always equal to 1, and alpha 1 is always equal to the mean of the distribution provided it exists. So you can use these two results in subsequent study. Similarly, if you put k is equal to 0 over here, you will get that mu 0 is equal to 1. And what about mu 1? If you put k is equal to 1, you will get that expectation of x minus m, that is actually mu1, and this can be represented as expectation of x. You see, we have a printing mistake. It should be the random variable capital X. Okay, so expectation of x minus expectation of m. Expectation of m is actually the real number m itself. Hmm. And what is expectation of x? Expectation of x is equal to m. We know that expectation of x is equal to m minus m. So this total value becomes is equal to 0 for any random variable. So for any random variable, whatever random variable you consider, the value of mu1 is always equal to 0 here. So these are the mean, the central, and the definition of central and raw moment, and we have a relation in between the central moment and raw moments. What is the relation? Sometimes this is also selected as a question, a very easy question in exam, that we need to find out the relation in between the central and raw moments. Okay, you see, central moments are the raw moments are defined in this way alpha k, and central moments are defined in this way mu k. So if we assume that both of these two central and raw moments of order k exist, then we have a relation that you see, this x minus m to the power of k. If we binomially expand this one x minus m to the power of k through binomial expansion, then that binomial expansion can be written in this way: summation I is equal to 0 to k minus 1 whole to the power of I, multiplied by k to the kci x to the power of k minus I into m to the power of I. You can check this. Total expression. So we shall have x minus m to the power of k, that can be written in this way. So now if we consider the expectation on both sides, expectation of both sides, you see this is a finite summation. So linearity on the expectation can be used. Linearity property of the expectation can be used. Hmm. So if we consider the expectation of left hand side, we will get mu k, that is the central moment. And over here, these are actually constants with respect to this expectation. Even this m to the power of I, this is also a constant quantity. So only we shall have the expectation of x to the power of k minus I over here. And what is this expectation of k minus I? This is actually the raw moment, and that's why raw moment of order k minus I. That's why we shall write it as alpha suffix k minus I. Got it? So we have alpha suffix k minus I, this kind of relation. Again, if you consider the converse category of relation, that means over here in this relation number 3, you find that if we know the values of this central moment alpha, alpha 0, alpha 1, alpha 2, then we can find out the value of this kind of moments mu1, mu2, mu2. So if you consider this raw moments, not central moment, the raw moments, then by the values of raw moments, we will be able to compute the values of central moment. Now we are going to deduce a converse category of result. You see, this x to the power of k, that can be written as x minus m plus m to the power of k. And then we can expand it through binomial expansion, and we will get this kind of relation: summation I is equal to 0 to k kci into x minus m to the power of k minus I multiplied by m to the power of I. So if you take expectation on both sides, on the left we will have the this raw moment alpha k, and this is a constant quantity. This m to the power of I is also a constant quantity. So only we will have this expectation of x minus m to the power of k minus I. Okay, and that expectation of x minus m to the power of k minus I will give us the central moment mu k minus I. So this is the relation where from the values of this central moments of order up to order k, you would be able to find out the values of these raw moments alpha k. And particularly this, if you put the value of k is equal to 0, then 1, then 2, then 3, you will find that you get this kind of relation, that mu2 is equal to alpha 2 minus m square. This is a standard relation. You can use this relation everywhere in the subsequent study. This is the deduction process of this relation. I am leaving this deduction process for you. And this kind of questions are also generally selected as a short question in exam, that mu3, prove that mu3 is equal to this kind of expression. So please remember this result: alpha 3 minus 3m alpha 2 plus 2m square. I am leaving this deduction as a homework for you. Similarly, mu4 can be written in this fashion: mu4 minus 4m alpha 3 plus 6m square alpha 2 minus 3m to the power of 4. I am leaving this deduction for you as well. So similarly, we can get any higher order relationship. Okay. That's all I wanted to discuss over here. These are the relations. I am leaving these relations for the homework, that alpha 3 can be written as the central moments. Alpha 4 can also be written as the central moments. So this much I wanted to discuss today. So thank you for being with me in this class.